Hello dear students, I am Dr. Moin. Today we are going to discuss IR spectroscopy. Students, this is part 2. In part 1, we have discussed about the basics of IR spectroscopy and modes of vibration. I will attach the link of the part 1 in my description, so if you didn't watch part 1, then you must need to watch part 1 first. So here are the contents of current video. We will discuss about the degree of freedom, and degree of freedom tells us that how many types of vibrations will be present in some molecule. We'll see the selection rule. Selection rule will tell us about that which vibration will result in the absorption of IR radiations and which vibrations don't absorb IR radiation. Then we'll see the Hooke's law. Hooke's law enables us to predict at what frequency, the absorption will be shown by any kind of vibration. And then we will see the sample handling, how our sample is introduced in the spectrophotometer. Now we are going to see how many vibrations are possible in some molecule. So total number of vibrations in a molecule depend upon the number of atoms in it. Means how many vibrations will be there, that depends upon the number of atoms present in that molecule. Now each atom has 3 degrees of freedom. Why? Because 3 coordinates, that is x, y and z, are required to describe the position of any atom in space. So we can say that each atom has 3 degrees of freedom. So for example, if a molecule has n number of atoms, so we can say it will have total 3n degrees of freedom. Now we have to divide these 3n degrees of freedom because there are 3 types of motion: translatory motion, rotational motion and vibrational motion. So we'll see now how many degree of freedoms are required for each individual type of motion. So out of these degree of freedom, means 3n degree of freedom, 3 degree of freedoms are required to describe its translatory motion. So 3 degree of freedom are required to describe its translatory motion, whether the molecule is moving in x-axis, around y-axis or z-axis. Now if we talk about the rotational motion, so if the molecule is non-linear, then 3 degree of freedoms describe the rotation of a non-linear molecule, while if the molecule is linear, then 2 degree of freedom are required to describe its rotational motion.
Since in IR spectroscopy, we are interested with vibrational degree of freedoms, and these can be calculated by subtracting the translatory and rotational degree of freedoms from the total degree of freedoms. So it means that 3n minus 6, 3n are the total degree of freedom and 6 degree of freedom are translatory plus rotatory degree of freedoms for non-linear molecules. So if we do this 3n minus 6, this will give us the vibrational degree of freedom, while for a linear molecule, the 3n minus 5, this will give us the total vibrational degree of freedom in that molecule. For example, we have a water molecule. You can see its structure. It's a non-linear triatomic molecule. So since it's a non-linear molecule, so we will follow the formula 3n minus 6, where n is the total number of atoms. So 3 atoms are present in water molecule. So 3 into 3 gives 9 minus 6. It means there will be 3 types of vibrations present in water molecule, and you can see it in the diagram. So these have been observed as symmetrical stretching, second one is asymmetrical stretching, and third one is the bending vibration, and that is the scissoring vibration. Then we take another example of carbon dioxide molecule. Still, there are 3 atoms in carbon dioxide, but this molecule is a linear molecule. So now we will follow the formula 3n minus 5. So if we put n is equal to 3, so total answer is 4, means there are 4 types of different vibrations present in carbon dioxide molecule. So you can see in the diagram, these are symmetrical stretching, second one is asymmetrical stretching, while rest of the 2 vibrations are the scissoring vibrations. Both of these vibrations are scissoring, and these are going to happen in different planes.
Now we'll see the selection rule. It is not necessary that every fundamental vibration results in absorption of IR radiations. Means not all vibrations cause absorption of IR radiations. So selection rule actually tells us that only those vibrations which cause dipole moment to fluctuate and thus produce a fluctuating electric field will interact with electromagnetic radiations. So selection rule actually tells us that those vibrations which cause dipole moment to fluctuate, this happen in polar type of molecules, only those interact with electromagnetic radiations. So such vibrations which interact with electromagnetic radiations, these are called IR active vibrations. For example, we can say carbonyl group. These the vibrations present in this group, they will be IR active vibrations. While the vibrations that do not cause the change in dipole moment, they do not interact with IR radiations, and they are known as IR inactive vibrations. For example, you can say you can see these nonpolar molecules like H2, Cl2, N2, etc. So now we can understand the absorption of IR radiation, which is going to happen due to different types of vibrations with the help of analogy of balls and springs. So just remind the spring which we use in our daily exercise. So we can say that it is easier to bend a spring than to stretch it. So this indicates that the stretching vibration of a bond requires more energy. So it will absorb at higher frequency than bending vibration. Here is an example. A CH stretching absorption, it occurs around 3000 per centimeter, whereas CH bending absorption, it occurs around 1400 per centimeter. So here you can compare both of these stretching and bending vibrations. Similarly, again remind that spring. So we can say that it is easier to stretch a single spring as compared to 2 springs or 3 springs. So this indicates that the absorption due to double bond should occur at the higher frequency, or absorption due to triple bond should occur at still much higher frequency. So the stretching absorption of C triple bond C, it occurs at around 2200 per centimeter. Then stretching absorption due to C double bond C, it occurs around 1600, and then C single bond C, it occurs around 900 per centimeter. Another thing, and that is stretching frequencies also depend on the masses of atom. So OH bond absorbs near 3600 per centimeter, and if we have the heavier mass isotope of hydrogen, that is deuterium, so OD bond absorbs near 2600 per centimeter. So we can conclude that greater the mass, so frequency of absorption will be lesser, and this thing will be explained in the next slide in the Hooke's law.
Now we will see the Hooke's law. Hooke's law is actually used to calculate an approximate value of stretching vibrational frequency of a bond. According to Hooke's law, The stretching frequency is related to masses of the atoms and the force constant of a bond by the following equation, where the force constant actually it is a measure of resistance of a bond to stretching. And what is the equation? We can see it clearly that the stretching frequency that is equal to 1 over 2 pi c into f over ma into mb over ma plus mb, and there's a square root. So actually this stretching frequency is due to some bond, and that bond is some between two atoms A and B. So now we will describe what are the things here. So C in the equation, that is the velocity of light, and that is taken in centimeter per second. F is the force constant of a bond, and its units are gram per second square, where Ma and Mb, these are the masses of atoms A and B, and these are the masses, these masses are taken in grams. Now the values of F, these are constant for single bond, double bond and triple bond, and these are actually 5, 10 and 15 into 10 raised 5 gram per second square for single bond, double bond and triple bond respectively. Now we will apply this Hooke's law for the calculation of the frequency of CH stretching vibration. And as I mentioned earlier, that the masses of atoms that will be taken in grams. So we know that mass of carbon is 12 AMU, while mass of hydrogen is 1 AMU. And we know that 1 AMU is equal to 1.66 into 10 raised minus 24 gram. So we can convert it into grams. So the mass of carbon in gram will be 19.9 into 10 raised minus 24 gram. And the mass of hydrogen will be 1.66 into 10 raised minus 24 gram. So now we will apply the Hooke's law, the formula 1 over 2 pi c into force F over ma into mb over ma plus mb and the square root. So we simply put all of the values. We know that 2 is a constant, pi is a constant, so the value is 3.143. Then the c is the velocity of light, and its value is 3 into 10 raised 10 centimeter per second. Now ch, because there is a single bond, so the force constant value will be 5 into 10 raised 5 gram per second square. And then there are the masses which we have calculated above. So then we'll see simple mathematical calculations, and the final stretching vibration of this CH bond that appears to be 3032 per centimeter. And the experimentally calculated CH stretching vibration that is observed around 3000 per centimeter. So what do you say that the Hooke's law, it actually helps us to predict that at what position the some bond will absorb. So in this slide, the regions of various stretching vibrations are summarized here in the form of table. So on the left hand side you can see the bonds, and on the right side there are absorption regions in per centimeter. So you can see the bonds like single bond like CH, OH, NH, and the absorption region is from 3700 to 2500 per centimeter, while the triple bonds like CC triple bond and CN triple bond, and their absorption region is from 2300 to 2100 per centimeter. Then the double bonds like CC double bond, CO double bond, CN double bond, so their peak appear generally at around 1900 to 1600 per centimeter. And the absorption due to CC single bond, CO and CN single bond, it generally appears around 1300 to 800 per centimeter. An IR spectrum may be divided into two parts. We know the whole region of IR spectra, and that is from 4000 to 625 per centimeter. So it may be divided into two parts. So the first part that ranges from 4,000 to 1,600 per centimeter, and it is called functional group region because the peaks due to functional group, they generally appear in this region, while the second part that ranges from 1,600 to 625 per centimeter, and it is called fingerprint region. Now we will see the sample handling. So what is sample handling? Actually, this is the technique used for mounting the sample in sample beam of IR spectrophotometer. And this depends on the nature of sample, that how we will introduce our sample in IR beam. So first of all, how to introduce gaseous samples. A gas sample is introduced into an evacuated gas cell. You can see below the diagram in which these gas cells have been shown, and these are made by Shimadzu. These cells are available in lengths ranging a few centimeters to meters. But our instrument that cannot accommodate cells longer than 10 centimeters. Then how to get path length in meters? So long path length cells, actually they have mirrors in their walls. So there is several time reflections of the IR radiation before it exits the cell. So in this way, the path length in meters can be achieved.
Then how liquid samples are introduced? A liquid sample is examined as a thin film squeezed between two optically polished circular flat plates of rock salt. So these plates are made up of sodium chloride, and these can be shown in the figure. The dimensions of plates are: their thickness is about 5 mm while their diameter is about 25 mm. So what do? Actually, we take a single plate, we put a drop of liquid sample on it, then we put second plate on it, we press both of these plates, and our sample is converted into a film of thickness of about 0.1 mm. Plates are held together by capillary action, and these are mounted in the path of sample beam, and in this way sample spectra is recorded. Then after use, plates are cleaned by chloroform. Plates are kept dry and handled by their edges. For those samples that dissolve sodium chloride, silver chloride plates may be used.
Then how to introduce solid samples? Solid samples are usually examined as a mole or as a KBR disc. So we will see them one by one. So first one is New-Joule mole method. Mole is actually a two-phase mixture. And how it is prepared? It is prepared by thoroughly grinding 2 to 5 milligram of sample in a smooth mortar with pestle, shown in the figure. Then we add in it 1 to 2 drops of mulling agent, that is in the form of liquid. We continue grinding the mixture, and finally we get a homogeneous paste. This paste is examined as thin film between sodium chloride plates, as I mentioned earlier. Now what is mulling agent? This is also known as New-Joule. It is a mixture of high molecular weight liquid paraffinic hydrocarbons. It is also known as high boiling petroleum oil. So this is used as mulling agent, also known as New-Joule. Another way of introducing solid samples is to convert your sample into potassium bromide discs. So how these are prepared? These discs or pellets are prepared by grinding and mixing about 1 milligram of solid sample with 100 gram of dry powdered potassium bromide in a smooth mortar. Then this solid solution is compressed under high pressure of about 20,000 psi in a special type of dye, and that converts it into a disc. And here is the dimension of the disc. The thickness is around 1 millimeter and the diameter is about 10 millimeter. These discs are handled by their edges and are put in the path of IR radiations, and in this way the spectra is recorded. And one of the benefits of using this potassium bromide is that it is transparent towards IR radiation. That is, it doesn't absorb IR radiations.
Now, if we want to introduce our sample in the form of solution, so we can also do it. So the solution of samples are usually prepared in carbon tetrachloride, carbon disulfide, or chloroform. Solutions are usually made in strength of 1 to 5%, and these are handled in the cells of usually 0.1 to 1 centimeter path length. This is actually centimeter. So one cell containing the sample solution, while the other cell that contains solvent, and it acts as a reference cell. Now solvent may also absorb in some region. So if whole region is to be studied, then we must have to run two spectra of the samples prepared in two different solvents. A common pair of almost complementary solvents is carbon tetrachloride and carbon disulfide. And how these are complementary to each other? Because when we run our sample in carbon tetrachloride, then CCl4 is transparent above 1333 per centimeter. Means we can study the peaks of our sample from 4000 to 1333 per centimeter, but not below that, because below that carbon tetrachloride absorbs strongly. So if we still want to study the region below 1333, so we must have to prepare another solution of our sample in some other solvent, and that is carbon disulfide, because carbon disulfide is transparent below 1333 per centimeter. So both of these two solvents are complementary to each other. We know that water and ethanol, these are also some good solvents, but these are not in IR spectroscopy, as they dissolve sodium chloride, which cause fogging on the plates.
So dear student, this is all about today's video. Thanks for watching. If you like my video, then like it, and if you didn't subscribe my channel yet, then subscribe it to get in touch with my upcoming videos. So thank you very much.